Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
The first talk in the session is on shrinking the search space for cluster planarity, and it will be given by Carsten.
Thanks, Stephen. So in this talk, I will give some new results on the complexity of the cluster planarity problem, and these are basically derived from graph theoretic reductions of the search space. And this work is done by Marcus Chimani and me, and my position is also sponsored by Tom Sawyer Software. So this was the obvious mentioning of the sponsor of the session. So the cluster planarity problem is a long-standing open problem, basically since clustered graphs have been introduced by Feng et al. In the 90s. And the clustered graph is just a standard graph together with an inclusion hierarchy that is given by a rooted tree, and the leaves of the tree are the nodes of the graph. And we would like to draw this clustered graph in a way that the clusters are nicely represented by some simple closed region, like in the drawing to the right. So cluster planarity now, in extension to planarity, covers some aspects that are introduced because of this inclusion hierarchy, which cannot be covered just by counting edge crossings. For example, if you look at this graph without any edges, if I add some matching edges to it, the graph is still planar, and I will tell you in a minute why I have this crossing here. Because now, using this inclusion hierarchy, we can add some clusters that make a cyclic structure out of this non-connected graph, and I can add a further set of clusters. And now, as you can see, we have a K3-3-like structure, which obviously is not planar, but the underlying graph still is non-connected, and it's planar. And I can even get rid of this crossing that would be needed for the K3-3 by just rooting the edge like this. But now I have an edge region crossing. This edge here goes through the middle region that represents one of the clusters, and we would like to avoid these when we talk of clustered planar drawings. The same thing can happen even if the edge leaves a cluster, because it can just re-enter the cluster and partition the cluster, for example, to go around such an obstacle. This is also an edge region crossing. There's a third kind of crossings besides edge crossings and edge region crossings that can occur in a clustered graph drawing when we have two regions that cross. So we have no edges that are involved here, but the regions cross, and all of these cases should be avoided when we want to have a clustered planar drawing. So the concept of clustered planarity basically requires that we have a planar drawing of the underlying graph. Each edge crosses the boundary of the drawing of a cluster at most once, which gets rid of the edge region crossings. And we have a so-called inclusion representation of the tree T. An inclusion representation is just a representation of each cluster as a simple closed region, such that the subtree rooted at the cluster is represented within this region. For the green cluster, for example, it has a brown and an orange child cluster and 3 vertices, and the brown and the orange child cluster regions are within the region for the green cluster, and also the vertices and edges in these child clusters. So C-planar drawings have a planar drawing of the underlying graph and the 2 additional requirements. There has been a lot of work for C-planarity. I don't want to go into detail for all of the classes, but I will shortly discuss one of these results, because we will use the concepts in the further discussion. And these are the completely connected graphs, which were introduced by Cornelissen and Wagner in 2003. A completely connected graph is a clustered graph where for each cluster, the induced subgraph of the cluster and the induced subgraph of the complement are connected. In this example, if you look at this cluster, the induced subgraph is connected, and also the induced subgraph of the complement is connected. And the same is also for the other two clusters, so this is a completely connected graph. Why is this a useful concept? Well, basically, this requirement gets rid of the two additional properties that we have for clustered planarity in addition to standard planarity, which is that we don't want to have edge-region crossings and region-region crossings. And so it's not a surprise that there's this result also by Cornelissen and Wagner stating that a completely connected clustered graph is C-planar if and only if the underlying graph is planar. So for clustered graphs that are completely connected, the cluster planarity is reduced to planarity again. So how can we exploit this result now? Using again a result by Cornelissen and Wagner, so it's a great paper, you should read it, which is basically saying that a clustered graph is C-planar if and only if it is a subgraph of a C-planar completely connected clustered graph, which means that we can try to find a planar completely connected augmentation of a graph, and if this augmentation exists, we know that the graph is C-planar, and if the augmentation does not exist, we know it cannot be C-planar. So that brings us to the following situation. We have this general problem where the complexity is unknown. We know that for this very restricted class of graphs, the completely connected graphs, the problem of finding the deciding clustered planarity equals planarity. And in between, we have an augmentation that could be possible. And the question that we can ask now is, what is the complexity of this augmentation? Obviously, if we can augment a graph to be completely connected, this augmentation should somehow capture the whole complexity of the cluster planarity problem. So we can ask questions like, which edges for the augmentation are always needed? So we have to add them, reducing the problem. Which could be needed, so they need to be in the pool when we search in our search space. Which are never needed, so we can just remove them from the problem. Or are there, for example, equivalence classes where we know we can just pick one of the edges, but we don't know exactly which one we need. So here comes our result into play. The search space reduction characterizes a set of sufficient edges, and especially a set that is smaller than the whole set of augmentation edges. So let's get into details. First, I will explain a couple of concepts before I explain our results. We want to achieve complete connectivity, augmenting a graph or trying to find an augmentation and then testing just planarity to find out if the graph is C-planar or not. So we have to achieve cluster connectivity for the cluster and connectivity also for the complement of the cluster. If we look now at a cluster, we have a couple of chunks, which is just the connected components of the induced subgraph, and we would like to connect these chunks. There are many versions to do that. For example, even for this single node, we can connect it to every other node in all other chunks. So there's a huge search space. And we can do that for all of the nodes and increase the complexity of our search space. On the other hand, if you look at the following situation, if you have sub-clusters in this cluster that connect already chunks, then we know, because we have to achieve the connectivity for all clusters, all of the subclusters will be connected. So as some of the chunks are connected now via the subclusters, for the bigger cluster, we don't have to care about connecting this chunk, for example, with this chunk, because they're already connected over the subclusters. So instead of connecting all the chunks, it is sufficient to connect these new substructures. This one here, which is connected over that subcluster, and this one here, which has 3 subclusters. And all we need is connect from top to bottom and not in between the different chunks. Because this is an important concept, we gave it a name. We call these subcluster connected chunks bags of a cluster. And instead of connecting chunks for connectivity, we know now that we only have to interconnect bags. I just used the term interconnect to distinguish between connecting in a bag and interconnecting different bags. So for connectivity, we interconnect bags. And a further reduction that we can do is have a look at this bag here. This has a connection to the outside. And imagine this connection would not be there. So what is the influence now of this bag to the overall C-planarity of the graph? If this bag is C-planar, and this one is C-planar, then I can just add it somewhere in this cluster, and I don't care where it is. It does not restrict the C-planarity of the remaining graph. And if it is not C-planar, the whole graph is not C-planar. So what I can do with this bag that does not have a connection to the complement of the cluster is just test it independently. So in the beginning, what we do is a partitioning of the input graph, removing all of the maximum bags that we have that are not connected to the complement of their containing cluster. And in the remainder, we just focus on the bags that are connected over vertices to the complement of the cluster. In the following, I will call these vertices outer active vertices. So this is for the connectivity. And if we remove the cluster, we want to achieve co-connectivity or connectivity of the complement of the cluster. Now here the same mechanism can be applied if there are subclusters or clusters that connect chunks in the complement. We know also, because we want to achieve connectivity of these clusters, that parts of the chunks in the complement may be connected by these clusters. And we don't need to connect if there's already a connection via a subcluster. We only need to connect this part, then the whole connected part here with this part, and that is all we need to do. So we have a reduction also for the connection of the complement of the cluster. And basically, it's the same concept as for the cluster connectivity, but to make sure we distinguish in the following between the bags that we have here and the structures we have here, we also give these structures a name. And the bags in the complement are called satchels of a cluster. These satchels are connected via inner active vertices to our cluster. Okay, so a lot of concepts. And our result on this slide basically is it is enough to interconnect the bags for connectivity and to interconnect the satchels for co-connectivity. And there are two types of connections that we can have for the satchels. The first one is a direct interconnection, which just means, for example, this satchel is connected via an edge to this satchel. And there can also be another interconnection, because there may be parts of the graph that are not satchels. That is, they are not connected to the cluster, but we can still connect the satchels via these parts so that the complement of the cluster is connected. And I call this interconnection indirect interconnection in the following. So now from the concepts to the results, the first result is a lemma that basically states instead of having a complete connectivity, it is enough to use the connectivity of the bags and of the satchels. How can we see that? Well, in the one direction of the equivalence, it's quite simple. If I have a completely connected augmentation, then obviously all the bags have to be interconnected and all the satchels have to be interconnected. The other way to show that we can achieve C connectivity, we can do a bottom-up induction in the cluster tree. First, we look at the clusters that don't have subclusters, like this one here, for example. And we know that then the bags are just chunks. They don't have other subclusters. So we just connect them. So this subcluster is connected. We do the same for this subcluster. And now these bags are connected chunks. And all we do is connect these bags now in the larger cluster. And what we have is the connectivity. So the same basically is for co-connectivity. We know that each bag is connected, and as the satchels are also basically bags, they will be connected. And also in our augmentation, they are somehow interconnected. And what we have to take care of now is only if there are other parts of the graph that are not connected, because they're not satchels, that we can planarly connect them to this part. So how can we see that? We do a top-down induction in the cluster tree and want to make sure that the complement of a cluster is connected. For the root of the cluster tree, that is simple because the complement is empty, so it's connected. And if we look at any other cluster and we assume that the ancestors are already completely connected, let's call this one C and the parent P, we have the following situation. The complement of P is already connected, and we have some satchels of C that are interconnected, and then there may be parts that are not connected so far. Where can these parts lie in the graph? They cannot lie here because then they are satchels. They cannot lie here because then they are connected to the complement. So the only way we can position them is that they are here. What does it mean that they are here? They don't cross cluster boundaries, which basically means they are independent. So I can just check them for C-planarity. If they are C-planar, I just put them somewhere in P and connect the whole thing, and I'm done. Okay, so this proves our lemma. What we now know is that we only need to connect bags and satchels, but we can further reduce our search space. Intuitively, we can do the following. We just use outer active vertices for the connection of the bags, and we use inner active or outer active vertices for the connection of the complement. So in this example, it would be these two outer active vertices are connected with each other, and these two are connected, and then the whole cluster is connected. And for the complement, we just choose a couple of vertices that are inner active, this one, and this one inner active to this cluster, and this one is inner active to this cluster. What we can get rid of are nodes that are inner active but deeper in the hierarchy than our cluster. So we only need inner active or outer active vertices that are at least at a level of this cluster. So the theorem, much less intuitive, is saying a clustered graph with a planar underlying graph is C-planar if there's a planar augmented graph that satisfies basically two criteria. The first one is the outer active bags of each cluster are directly interconnected using only outer active vertices, and the satchels are interconnected using only vertices that are either inner active or outer active with a level not deeper than the level of the cluster. So I guess as I only have 1 minute, I just skip the proof and come to our last result, the fixed parameter tractability. We have now shown that we can use a shrinked set of edges for the augmentation. And now imagine we have a bounded number of inner or outer active vertices. Then we know that we only have a bounded number of possible augmentation edges, and also this gives us a bounded number of augmentations. And for each augmentation, the problem of deciding C-planarity is just to decide planarity, which means if you have a bounded number of augmentations, we can basically decide C-planarity in linear time. Okay, so to conclude, we have a way to shrink the search space for C-planarity testing. Sorry, I need some water. We have a FBT algorithm based on that, and we have a ILP-based implementation of our approach in OGDF. And what we would like to do is give better characterizations of needed substructures, for example, not just based on edges, but based on paths. And also use further structural information like tree-connected components, which partially fix the order of edges, and this could also lead to further reduction of the search space. And also we had yesterday this alpha, beta, gamma drawings, and I think this is somehow related, but I'm not really sure how it is related. So this should be something to investigate. And the conjecture is that C-planarity, I don't know. Okay, I guess that's it. Thanks.
Welcome to my talk. I'm Martin Gronemann, and this is joint work with my supervisor, Michael Nger. And I will talk about similar topic than Carsten, drawing clustered graphs, but as maps, more specific topographic maps. As an introduction, I will tell a small story how we actually came up with this idea. It was not like that we wanted to draw clustered graphs. It's more that we started with hierarchical clustering. And what Carsten referred to as this inclusion hierarchy is drawn to the right. So that is what you get. You can see the edges. And the question at some point is you do not only want to cluster a network, you want to see the result. And most of these methods, they are rectangle based, and that works for smaller instances. But if the hierarchy gets deeper and the number of nodes increases, this is a bit difficult to look at. And then at some point you start about what happens if I draw a cluster graph by hand, and you end up with this inclusion representation. And if you add colors to them, you use map colors, you end up with a topographic map. This is the result, is a small graph, result of our method, and it follows a basic principle. So nodes in different clusters are separated by a valley or water, so something that is lower than the nodes. And in the same nodes that are in the same cluster, they are on the same plateau or elevation level. Why is this in general a good idea? Topographic maps are easy to understand. Everyone knows them. Even people outside CS, so you don't have to explain them the whole hierarchy thing. And this turned out to be an advantage that we were not intended to have. This is the outline of the talk and of the algorithm. So I will not talk about the clustering. I will just talk about the layout. That is a tree map approach, and how you can obtain a triangle mesh that describes the elevation. And this is in the end used to do the edge routing as well. Okay, let's start with the tree map. Tree map is a very simple thing. You have, in our case, a binary weighted tree given. And our tree maps, unlike the one that showed Snellman before, are based on convex boundary, on convex polygons. So you start to recursively subdivide the polygons, and the area, of course, has to be proportional to what you want to fit inside this polygon. And this is a small example. You can see how we recursively split this. And in the end, you get a nested structure of convex polygons and not rectangles. And the graph nodes that form the the leaves of the cluster tree are just placed in the centroid of their corresponding polygon. Yeah, the question is, how do you partition such a polygon? You know that you have to make a cut somewhere so that the area is proportional, but you want a nice shape, so you don't want any very thin polygons, and nice shape is defined as small aspect ratio. That basically means that you want as much area, but still with a low diameter. The diameter is the maximum distance of two vertices. This partitioning, or this how you cut the polygon, basically is only then defined by the orientation of this cutting line. And we use the fat polygon partitioning of de Berg et al. I will not talk about how this actually works. Okay, we have a layout for the nodes, and what we now do is we generate a triangle mesh for the elevation model. And in the beginning, we apply a Delaunay triangulation that is constrained by the boundary polygon. So the black dots here are Steiner vertices. And when you now consider a triangle in this triangulation, there are basically two options. Here the triangle, all three vertices of the triangle correspond to graph nodes in the cluster hierarchy, so to leaves. On the boundary, there are these Steiner points from the Delaunay triangulation. We think of them as part of the root. So they're similar to the corner points. This will be the boundary of the map. So when you now consider the edges of such a triangle, they induce a path in the cluster tree. And they do not only induce a path, there's the lowest common ancestor for each of these three pairs. And what we do now is we refine this mesh further and actually insert representatives for these cluster nodes. So we subdivide a triangle into four subtriangles, and on each of the edge we insert a new vertex that represents the lowest common ancestor of the two endpoints of that edge. Here on the right you can see how it looks for the complete mesh. So far we did everything in the plane, but we want a topographic map, and the topographic map is usually modeled by a 2.5 D mesh. So what we now do is we are going to lift this mesh, and to do that we first assign the tree nodes an elevation level. And to think about that, you better turn around the tree so it looks like this. So the root is the lowest point on the map, and then here these clusters, they are going to form mountains, and on top of that later the nodes are located. Okay. Now the idea is straightforward. We just take these elevation levels and transfer them to the mesh, and this results in the 2.5 D mesh. For the final drawing, we rasterize the mesh, so you get an image, a raster image, and you can do this with cubic Bézier triangles to get smooth boundaries. And I will, if I have time, I will tell a bit more about this step. I did it here by hand, so this is what it looks finally. Okay, so what is missing? The edges are missing, and the idea is straightforward now. So what we can do is we use the mesh that describes the landscape to as a routing network for some shortest path based edge router. And yeah, for those who don't know about that, it's very simple. You have an edge here in the graph to the left, and you have two graph nodes in the elevation mesh, and you compute a shortest path just from the starting node to the end node based on some distance metric. Yeah, to have smooth curves, like we use the cubic Bezier triangles for the elevation map, the nodes found on the shortest path from the source to the target nodes, they are just used as control points for a quadratic curve or something like that in the final drawing. Okay, one problem. So when you consider this red edge here from A to D and the shortest path from A to D in the routing network, you notice that there are some unnecessary turns. While you can get from C to D in a nearly straight line, this does not work for A and D. And what we do now to solve this problem, we insert additional edges. So A is adjacent to two cluster nodes, the green and the gray one, but not to the third of that triangle. And we just insert this edge now, and as a result, you get a straight line. This is just to compensate for the problems during the subdivision. Okay, the thing is that this is on the right, you can see it how it looks for the complete mesh. I skipped some parts on the boundary. But the problem is with the distance function for the shortest path query. These newly inserted edges, they allow shortcuts. It's not really shortcuts, it's more that these edges might serve as a bridge over a valley. And so we split the distance function into the Euclidean distance in the plane, and yeah, it's more like the tree distance. So the edge, an edge has not, when it's kind of a bridge, you have to account for the complete way you go down the valley and up, and you have to account for that. Best example here is if you go from B to this node, you are crossing this valley here. And if you just take the Euclidean distance, you're not going to account for that. Yeah, this is the final drawing with all edges routed. And yeah, I described the tree map layout, the triangle mesh, and the edge routing. And this leads to this elevation model as a raster graphic, and the edge layout in forms of control points for a curve. And what we did then is we put all these things into tools from cartography to, which are usually used to draw real maps. So instead of using something from graph drawing, we went for something that produces real maps. And for the graph drawing collaboration network, it looks like something like this. And if you go down this road even further, you can get something like Google Maps. It's very interesting that while you are doing this, there are a lot of common things between cartography and graph drawing. Especially, you can save a lot of work. And yeah, you can try it. It should work. You can search for things. It's searching for people, and it searches the abstract of most of the graph drawing articles. So I think until 2011. And yeah, it works like Bing or Google Maps. So it's quite easy to use. Yeah, ongoing and future work. One can argue that the tree map approach has the big problem that it does not care about the edges. And that's true. It does not care about the underlying edge set of the graph at all. So these are two pictures from an application in chemistry. And there's the problem that the hierarchy is part of the input. So in the original approach, the clustering is part of the layout. So there's an indirect link between the edges and the tree. And this is not the case here. And we had to do something about it, and we modified the partitioning approach so it takes the underlying edges into account. And this works quite well. There is probably a bit of improvement, but in general, it works quite nice. The other thing is the shoreline. You notice that there is a very big difference between water and land. In the GD map, this has no meaning at all. It does have a meaning in this application from chemistry, but yeah, we are working on this, so probably the max modularity communities would be a good idea to set the water level at. And the third most important thing is that the edge routing. There are two problems. That is the visual appearance. You can see here that it's really hard to follow edges. The other thing is the runtime. The runtime is not acceptable for larger graphs. It's in the end something like all pairs shortest path, and yeah, it's not practical. There are probably ways to improve that, but this question should be answered first. So what we did is we tried something totally different, like hierarchical edge bundles from Danny Holton. And yeah, just to resolve this problem by moving these bundles into real parallel bundles from the, but this is not, yeah, it's still in development and it's not that nice. So if there are any suggestions, I would be really happy to hear about that. Okay, that's it.
Martin. Do we have time for questions? Questions? I have a question. Are you filtering out some of the edges? When you're showing a map of the GD collaboration and so on, were you filtering out some of the edges?
No.
You were showing everything?
Yeah. Yeah, but still that is a very sparse graph. And I tried, for example, this composer's graph from, was it last year? The GD challenge. And that looked really horrible. So
you may need to remove something.
Yeah, I have to do something about it. Even if you have something like hierarchical edge bundling, it's still too much.
Other questions? Thanks, Matt.
I'm Suraj Alamdari. This is a work with Biedl about rectangle of influence drawings. I will get to what they are in a second. So just a review of the basics. So a planar drawing is a drawing with no crossing. A planar graph is a graph that has some planar drawing, and a plane graph is a planar graph with a fixed embedding. And a straight line drawing is a drawing in which all edges are a straight line segment. So, okay, we hopefully know this. So, what's the rectangle of influence drawing? A rectangle of influence drawing is a straight line drawing in which the axis aligned rectangle for each edge, the axis aligned rectangle that has that edge as its diameter is empty in the sense that it contains no other vertex. So for example, this is a rectangle of influence drawing. This is true if we consider open rectangle of influence drawings, if we consider the rectangles to be open. But this is not because of this rectangle and the edge that contains it. induces it. So it has been studied in strong and weak senses, closed and open, exact and approximate. Approximate will be the next talk, the subject, I believe. And so, yeah, so this is the this talk is the continuation of the talk, the work of our work last year, which was in turn inspired by a work of Miyotaro, Matsuno, and Nishizaki. So we want to characterize RI drawings. So RI drawing, I mean by RI drawing, open, weak, planar, rectangle of influence drawings. So the goal is to test if a given graph G has an RI drawing. So we studied the problem for plane graphs and planar graphs. For planar graphs, we proved the problem to be NP-hard. For plane graphs, we can't, well, solve the problem, so we change the problem. So we add some properties to the RI drawing that we are looking for. Then we can solve it.
Sorry, have you told us what weak means?
Weak, OK. So I didn't tell you what strong is. So yeah, so weak is what I just said. But the way I introduced it was weak. So a strong RI drawing, in a strong RI drawing, if an edge could exist, should be there. So yeah, so I will be talking about weak RI drawings in the talk. So thanks for asking. Yeah, before going to RI drawing, I want to introduce a labeling. Type of labeling may be useful. So we label the angles of a straight line drawing by just counting the axes inside each angle. So here we would have labels 1, 0, and 3. And this, so what happens if we have an axis-aligned edge? So we assume that edge contributes half a point to each of the two angles that it appears to. So for example, here we have 3.5 and 0.5. So this type of drawing captures the properties of some other labelings that have been proposed for angles, angular labelings. So might be of interest. So and they are uniquely defined for each a straight line drawing. So let's go back to rectangle of influence drawings. We will first let's look at the simplest type of graphs that we can look. The graphs that have a triangular outer face. So if we have a triangular outer face, the outer face basically forbids us to place the points anywhere that is hashed here. So the only place that vertices can be are on the green lines here. So the vertices that are inside the triangle. So I'm drawing the graph above down there as an RI drawing. So if we don't, so let's put alpha aside. The rest of the graph basically should be drawn on two lines. And that's not hard. So drawing a graph on two lines would require us to find a chain of cycles. That's not hard and can be done. So basically, we can find an RI drawing if the outer face is a triangle. And more than that, we can check we can find all the axis count labelings that are realizable, axis count labelings of the outer face that are realizable in a rectangle of influence drawing of the graph. So for graphs that have triangular outer face. So let's go to general graphs. So scary, a bit scary. Yeah, so what we do is that we first, so I will just overview the algorithm. What we do is that we remove the inside of field triangles, the triangles that have stuff inside them, so that the graph is simplified. It has no field triangles anymore. And this doing this, we have some angles that are forced to have axis count label 1 in the final drawing. If we respect these forced labels, in the end, we can put back in whatever we removed in this step. Next step, we switch to the dual space. Well, some graph that is defined somewhat weirdly, but it has a vertex for each triangular face and a face for each non-triangular face. So the blue graph is the graph the dual-like graph. And we translate the labels that should have axis count label 1 in the final drawing to the corresponding labels of the dual-like graph. So we'll have a graph in dual space with some of its angles marked. So this is the a step of the algorithm that will fail if we cannot draw our graph as an RI drawing that satisfies those conditions. So basically, we check if this dual-like graph admits an orthogonal drawing that satisfies some properties that I'm not going to go into exactly. But for example, the labels that we had marked should be right angles. So, and this can be done in polynomial time, this orthogonal drawing with some angles restricted to be right angles can be done in polynomial time. So if this step fails, there is no RI drawing that we want. So, but if this step goes through, we have an orthogonal drawing without bends. And the next thing we do is that we add some edges to the graph and vertices so that the graph becomes a rectangular drawing. From this rectangular drawing, we go back to the primal. So remember that we are in the dual space somehow. So we go back to we take the dual of this thing, except for the outer fixed vertex. So this graph now is a supergraph of the original graph that we had, not original, after removing inside of field triangles. So now what we do is that we use the structure of the rectangular drawing to extract a labeling for this new graph that we have, such that that labeling is realizable as an axis count labeling of an RI drawing. So the way we do it is that for each angle, we count the number of right angles that angle faces. So for example, here, we'll have 1 for this angle, 0 here, 1, and 2 here. The labeling that is extracted has some good properties. So there are Meijer give some properties of a labeling of angles of a graph that if those properties are satisfied, then that graph can be realized as an RI drawing such that that labeling is the axis count labeling of the drawing. The labeling that we extracted satisfies these properties. So we use their algorithm to construct the RI drawing. Then recall that some of the faces, we add some faces to the graph that turned into some of the vertices of this graph that we already have. So we need to remove those dummy vertices. This is the frame graph, the graph with the inside of field triangles removed. Now, what we have is that the angles that we marked have now axis count label 1. So we can put back in, so because we have respected this property throughout the construction, we can put back in the vertices of the field triangles that we removed. So by the algorithm that I initially explained for graphs with triangular outer face. So each of these triangles can be filled with that algorithm, using that algorithm. So we have an RI drawing of our initial graph. So let's look at, so this was for plane graphs. Let's look at planar graphs. For planar graphs, we have much more freedom of how we embed the graph. We actually embed the graph. And for example, for orthogonal drawings without bends, the problem is NP hard. Garg and Thomas show that it is NP hard. We use the same idea. We use the same approach to prove that this problem is RI drawing, open RI drawing of finding open RI drawing of planar graphs is NP hard. The reduction is from not all equal 3 sat. So the idea of the proof is that the idea of the showing hardness is that, so this is what appeared in their paper too. So is that to construct a graph that with a component with a subgraph that is attached to the rest of the graph through two vertices and is connected enough so that it has only one, it admits only one embedding and it's flip and it's mirrored version. So, and these two drawings will give us a truth assignment to our variables. So each of these such components will be corresponding to a variable, a truth assignment to a variable. So yeah. So review, what we prove is that what we give is an algorithm to test if a given graph has an RI drawing that satisfies the non-aligned frame property. So this is the property that we added. We needed to add the non-aligned frame property. This is not a natural property, but is not very restrictive. It doesn't happen very often. So yeah. So for plane graphs, this is what we have, non-aligned. We need it for the proof. We can get rid of it. And the running time is n to 1.5. For planar graphs, we prove that the problem is NP complete, even if we add the non-aligned restriction. So for the non-aligned case, the question is like solved, basically, this specific question. So yeah. Yeah. So two questions that remain are other faster algorithms. And so this one is good if it can be done. Can we get rid of the non-aligned constraint? We tried, we couldn't. Yeah, I finished early. Thank you.
Thank you. Questions?
Is it obvious that the problem lies in NP?
It's not obvious. The reason, so the reason for that is that the only thing that you need to specify for an RI drawing is the order of vertices, and that can be given. So you don't need to. If you give me the order of vertices in horizontal and vertical directions, I can tell you if that's an RI drawing or not. You don't need to. So then, therefore, it is in NP.
Is that some type of special algorithm, or is that?
No, it's not. So the only thing that you would need to see if a vertex is inside a rectangle defined by two vertices is that it is between both in horizontal and vertical ordering, the vertex that we want to see if the be between the two, the other two. Do you see what I mean?
Other questions? I saw another hand earlier.
I didn't quite understand how you moved to this strange kind of dual in the beginning. It seemed to have very many vertices. The blue.
Yeah. So I tried to, like, I thought it would take long, so I tried to be fast. So what we do is that for each triangle, we leave the triangular faces as they are. For non-triangular faces, we add a vertex inside each of them. And for each instance of a vertex on a non-triangular face, we add 3 parallel edges to that dummy vertex that we added. So here you see for example, for this instance, for example, this vertex has 2 instances of on the outer surface, so it has 6 edges to the dummy vertex. Now we take the dual. So the reason for this is that when we are drawing our rectangular orthogonal drawing, we want this edge to be able to bend. So we need these parallel edges.
Other questions? Let's thank our speaker again.
Good afternoon. This work is a joint work with Biedl, Liotta, and Meijer. It is again about rectangle of influence drawings, but here we study an approximate version of the problem. So let P and Q be 2 points in the plane. The rectangle of influence of P and Q is the rectangle rho P and Q having P and Q as opposite corners. So this is the rectangle of influence of these 2 points. And if the boundary of the rectangle is considered to be part of the rectangle, we say that it is a closed rectangle of influence. Otherwise, we say that it is an open rectangle of influence. And then a rectangle of influence drawing of a graph is a straight line drawing such that for every edge U and V, the rectangle of influence of U and V does not contain any vertex distinct from U and V. And for every pair of non-adjacent vertices U and V, the rectangle of influence contains at least another vertex. So this is the strong version of the problem. So for example, this is a rectangle of influence drawing. You can see that for the existing edges, the rectangle of influence are empty, while for non-adjacent vertices, the rectangle of influence contains some other vertices. Okay, this type of drawing has been introduced and studied in this paper by Liotta et al. In 1998. And in this paper, they characterize the graphs, drawable graphs, according to the rectangle of influence drawable graphs in some families, like wheels, cycles, trees, other planar graphs, and so on. I will not enter in the details of the result, but what is interesting for our paper, for this talk, is that the class of graphs that can be drawn is very restricted. I mean, not all cycles, not all trees, not all other planar graphs can be drawn. So if you want to draw something more, you need to relax the problem some way. And one possibility is to use the weak version of the problem, where you just require that for the edges, the rectangle of influence does not contain anything, while you don't care about non-adjacent vertices. And we have seen the previous talk about this. Another possibility is to use the approximate version of the problem. And the approximate proximity is a concept that has been introduced last year in a paper by Evans et al., where a general framework for the study of approximate proximity drawing has been introduced. And so we will study the problem within this framework. So let me define what is an approximate rectangle of influence drawing. So let rho P and Q be the rectangle of influence of P and Q, and let epsilon be a given value. The epsilon expanded, the rectangle of influence of P and Q, is the rectangle obtained by enlarging rho P and Q by a factor 1 plus epsilon. While the epsilon shrunk rectangle of influence of P and Q is the rectangle obtained by shrinking rho P and Q by a factor 1 over 1 plus epsilon. And now we so this is a rectangle of influence. This is the expanded version. That one is the shrunk version for some epsilon. And now we can define an epsilon 1, epsilon 2 rectangle of influence drawing of a graph. It is a straight line drawing with the following property. For every edge u and v, the epsilon 1 shrunk rectangle of influence does not contain any vertex distant from u and v, and for every pair of non-adjacent vertices, the epsilon 2 expanded rectangle of influence contains at least one vertex. So the idea is that for the adjacent vertices, I use a smaller rectangle, and for non-adjacent vertices, I use a larger rectangle. So this makes my life easier. And so let's look at an example. This is not a rectangle of influence drawing because these two vertices are not adjacent, but their rectangle of influence is empty. And these two vertices are adjacent, but their rectangle of influence contains something. But if we choose epsilon 1 and epsilon 2 equal to 0.5, we have that the expanded rectangle of influence of that 2 point contains the whole drawing, so contains some other vertex, and the shrunk rectangle of influence of these 2 points does not contain anything. So this is an epsilon 1, epsilon 2 rectangle of influence drawing for epsilon 1 and epsilon 2 equal to 0.5. Okay, so we study what graphs admit an epsilon 1, epsilon 2 rectangle of influence drawing for different values of epsilon 1 and epsilon 2. And we also investigated the area of the drawing. In particular, we investigated whether it is possible to obtain polynomial area in some cases. Okay, this is the list of results. First of all, we proved that every planar graph has both an open and a closed epsilon 1, epsilon 2 rectangle of influence drawing for every positive epsilon 1 and epsilon 2. So if epsilon 1 and epsilon 2 are positive, we can draw all planar graphs. On the other hand, if one of the two parameters is 0, either epsilon 1 or epsilon 2, there exists planar graph that cannot be drawn. And so, motivated by this result, we investigated the case when one of the two parameters is 0. In particular, we concentrate on the case when epsilon 1 is 0. And we study other planar graphs. So we proved that every other planar graph admits both an open and closed 0 epsilon 2 rectangle of influence drawing for every epsilon 2 larger than 0. But the drawing has exponential area. So we try to reduce the area. And we can do it for every other planar graph. So every other planar graph has a drawing in n to the fourth area. But we need that epsilon 2 is more than 2. And if epsilon 2 is less or equal to 2, we are able to draw only binary trees. Again, in polynomial area, the area is given by that formula where the exponent depends only on epsilon 2. So for fixed epsilon 2 is a constant. Okay, so in the remaining part of the talk, I'll try to give you the idea behind this, the idea of the technique behind these results. Okay, let's start with planar graphs and positive epsilon 1 and epsilon 2. Here the technique is very simple. The idea is to construct the drawing of vertex per time according to the canonical ordering. So at some point I've drawn the graph induced by the first k minus 1 vertices, and I have to add the kth vertex vk. And the idea is to place it sufficiently far from the existing drawing. And what does it sufficiently far means? Well, consider one vertex in the existing drawing. If I place vk very far, I have that the expanded rectangle of influence of these 2 points contains the whole drawing. And at the same time, the shrunk rectangle of influence does not contain anything. So basically, I can decide, I can connect vk to this vertex or not. I can choose. And so I can connect vk to all its adjacent vertices. And with some geometry and some math, you can see that the distance that we need is given by this equation. And these two terms depends on epsilon 1, epsilon 2, and on d, which is the diameter of the existing drawing. There are some other technicalities, but basically this is the idea. Okay. Let's look at other planar graphs. Okay, in this case, epsilon 1 is 0. So for the edges, I consider the usual rectangle of influence. For the non-adjacent vertices, I use the expanded rectangle of influence. Here, the idea is to compute, to compute a BFS tree of the graph. to draw the tree and then to add the remaining edges. So this is another planar graph. The bold edges define a BFS tree, and this is another drawing of the same graph. Okay, now in order to draw the tree, I first draw the star induced by the root and its children. And to do this, I choose a real number p, such that p is at least 2 over epsilon 2 plus 1. And then I draw u, the root at the origin, and draw the child number I at a point with coordinate p to I minus 1, p to k minus I, where k is the number of children. And so, for example, for 6 children, I have a drawing like this, where here p is 2. And in this drawing, you can see that for the edges, the rectangle of influence is empty. So the edges are, can be there. And now consider 2 non-adjacent vertices, in particular 2 consecutive children ui and ui plus 1. Well, we have that the width and the height of the rectangle of influence, delta x and delta y, are given by these 2 equations, by these 2, okay. And if you now consider the expanded version of the rectangle, and we consider this enlargement, this delta x prime, we have that delta x prime is epsilon 2 over 2 times delta x. And doing some math, you can prove that this is larger than p to I minus 1. But p to I minus 1 is the x coordinate of this point. So this means that this distance is more than the distance of this point from the y-axis. And analogously, you can prove that this distance, delta y prime, is more than the distance of this point from the x-axis. And this means that the expanded rectangle of influence contains the origin, so contains the root of the tree. And so these 2 points can be non-adjacent. Okay, now we have drawn the first 2 levels, and we can draw the subtrees rooted at each child recursively inside these boxes. And these boxes must satisfy this condition. I mean, the dimension must satisfy this condition. And again, I will not enter into detail, but if you satisfy this condition, you can prove that choosing a vertex from a subtree, say ti, and another vertex from another subtree, say ti plus 1, their expanded rectangle of influence contains ui and ui plus 1. So the 2 points can be, the 2 vertices can be non-adjacent. Okay, so this is the drawing of the tree, but now we have to add the edges of the other planar graph that are not in the tree. And since this is a BFS tree, since this is another planar graph and we perform a BFS visit, the edges are either between consecutive children, like 2, 3, and 4, 5. Yeah, 2, 3, 4, 5. And then in this case, the rectangle of influence is empty. Or you can have edges connecting consecutive vertices that don't have the same parent, like, say, 10, 11, or 12, 13. And also in this case, you can prove that the rectangle of influence is empty. And also you can have edges like this one, 12, 4, so from different level, but again, consecutive points. So also in this case, you can prove that the rectangle of influence is empty. Okay, so this is the technique for other planar graphs. And it's immediate to see that the drawing has exponential area. I mean, even the drawing of the star has exponential area. So we want to try and reduce the area. And as I said, we can do it for all other planar graphs if epsilon 2 is more than 2. And indeed, the technique is slightly more general because we can draw not only other planar graphs, but proper track planar graphs. And proper track planar graphs are basically level planar graphs. So the vertices can be placed on levels in a planar way. But the edges can be only between consecutive levels. And this is the meaning of the word proper. But on the other hand, we allow edges within the same level. And this is why I call these graphs track planar instead of level planar. But notice that since the drawing must be planar, the vertices within the same level must connect consecutive vertices on the level. And it's easy to see that other planar graphs are proper track planar graphs. Okay, now if I have a graph like this, I draw it this way. I place the vertices of the first level on x coordinate y 2, 3, 4, 5, and on y coordinate 5, 4, 3, 2, 1. So they are on a straight line with slope -1. Then I place next level similarly on another line with slope -1, and so on. And then I add the edges, and you can see again that the rectangle of influence of the edges is empty. I mean, it's immediate for these edges because the 2 points are consecutive. There is nothing in the middle. But it's true also for vertices on different level because this rectangle is contained in the strip defined by the 2 lines with slope -1. What happened for non-adjacent vertices? Okay, consider, for example, these 2 vertices. They are not adjacent. Since epsilon 2 is more than 2, the expanded rectangle of influence contains the 2 neighboring vertices 12 and 15. And so the 2 points can be non-adjacent. And you can prove that also non-adjacent vertices on different level, I mean the expanded rectangle of non-adjacent vertices on different level contains some other vertices. So this is the technique. It's very easy, but what is the area? If you look at the drawing that I showed you, the area is n squared because it is n minus n times n minus n. So where does the n to the 4th come from? The problem is that I didn't say the truth. Because I told you that if I consider these 2 vertices and I consider the expanded rectangle of influence, it contains the neighboring vertices. But what happens if these vertices are not there? So what happens if the level has only 2 vertices? Well, in this case, the algorithm doesn't work. Of course, we can fix it, this problem. But to fix it, we have to enlarge the drawing, and we get the n to the 4th area. OK, let's move to the last result, binary trees, epsilon 2 smaller than 2. And this is the more complex technique of our paper. We use a recursive drawing technique based on a greedy path decomposition. A greedy path is a path in the tree that goes from the root to a leaf, and is constructed this way. I start from the root, then I choose the subtree with more vertices, and I continue constructing the path in that subtree. So I go to U2 because it is the root of the largest subtree. And then analogously, I go on, and I have a path, and a set of subtrees attached to the path. Okay. And a set of subtrees attached to the path, and then I can recursively decompose the subtree. So now the drawing technique, the idea of the drawing technique is to draw the path, and then to attach to the path the drawing of the subtrees computed recursively. And we assume that the drawing of each subtree, the drawing gamma I of each subtree, satisfies 3 invariants. Okay, first of all, it is a valid drawing. The second one is that the root of the tree is on the left border of the drawing, and there is nothing below it. And finally, the drawing is completely contained in a bounding box whose dimensions are bounded by these 2 functions. Okay, so now we place the vertices of the heavy path on a straight line with slope -1. And we attach the subtrees to the path. So here, the first subtree is gamma 0, and we place it at a vertical distance, which is 2 over epsilon times the height of the drawing. Then we place next one, and we have that this distance is 2 over epsilon times the maximum between the 2 width. And this distance is 2 over epsilon, the maximum between the 2 height, and so on. We have some special case when the subtree has only 1 vertex, but in the end, we have something like this. And now, you can see that for the existing edges, again, the rectangle of influence is empty. This is easy to see for these edges and for these edges. And for the vertical edges, it is also true, because in the case of the vertical edges, the rectangle of influence coincides with the segment. And by the second invariant, there is nothing here, no vertex here. And so it's OK. Now, if we consider non-adjacent vertices, things are slightly more complex because there are many cases to consider. I will show you just one case. So suppose I have a vertex in gamma 0 and a vertex in gamma 1. Well, the rectangle of influence of these 2 vertices contains the rectangle of influence of P and Q of these 2 points. And if I look at the rectangle of influence of P and Q, its dimensions are delta x and delta y, and the enlargement delta x prime and delta y prime is given by this equation. So delta x prime, for example, is epsilon over 2 delta x, which, according to the choice of this distance and this distance, is according to the choice of this distance, is more than both the width of the 2 drawings. And analogously, delta y is larger than the height of the two drawings. And so the expanded rectangle of influence contains both subdrawings, and so these 2 points can be non-adjacent, but I mean, every vertex here and every vertex here can be non-adjacent. Okay, about the area, according to invariant 3, the drawing is contained in a bounding box whose dimension is this, and with some calculation, you obtain that the area is this one. Okay, some open problems. Okay, the first obvious open problem is to prove, to devise a technique to compute drawings with polynomial area for general planar graphs when epsilon 2 is smaller than 2. I mean, when epsilon 2 is smaller than 2, we can only draw binary trees. So it would be nice to draw all other planar graphs. Then we studied the case when, epsilon 1 is 0 and epsilon 2 is larger than 0. And in this case, we study basically only outer planar graphs. So it can be interesting to study other families. We have some further result in this, some simple result in this case. And finally, we can study, it would be nice to study the symmetric case when epsilon 1 is larger than 0 and epsilon 2 is 0. And also in this case, we have a very simple result. But, okay. Thank you for your attention.
Questions for Emilio? I have a question. Given the practical applications, are there any experiments on perceptual, when you look at weak, strong, approximate?
No, not that I know. I mean, we didn't make an experiment, and I think they have never been done. I don't know.
Anything else for Emilio? Thanks, Emilio.
Thank you for coming. So this is going to be talking on graphs and maps, looking at dynamic data, particularly on an area with regard to social networks. We had some discussion on it earlier today. Okay, so again, as been mentioned earlier, looking at online social networks and then data involved that is a very hot topic. It's been mentioned several times in various contexts. But there's a problem. For example, this is a trace of a listing of various tweets coming in over a small period of time. So it goes on and on and on and on and on, and it keeps these companies. And there's these millions of people out there constantly tweeting to each other. You know, how they could spend their time better, I don't know, but you know, they're doing it. Okay. So, for example, if you're just looking at the tweets that contain the word news, we are seeing up to like 34,000 tweets per hour on these things. Okay. Now, this isn't big data per se, but it's certainly pleasingly plump data. Okay. And so the question is, is there some way that we can use visualization to help to handle this, to analyze this stuff, to get a handle on this thing? All right. So this is where I do a brief change here. And pull that down. And with luck, it'll still be here. Yes. Okay. So this is going to be a top-down talk. I'm not going to tell you all the stuff and hear pieces, and to the end I get you to the conclusion. We're going to start with a chase. Okay. This is a little piece of software we put together called Twitterscope, and the idea is that it's going to give you a chance to look at a view of data from a dynamic flow of tweets coming in. You know, for every tweeting on a very particular topic. So you pick a particular term, and we're looking for all tweets that contain that term. And we're trying to analyze these things and see how do they cluster together and how they are related. Now, we have built in this thing a few basic topics. So let's just start with, say, for example, visualization, which seems to be appropriate. And what do you mean? Oh, dear. I don't see Bing on there, do I? Okay. Internet Explorer, sorry. Dear, dear, dear. Okay, well, this is going to be a faster demo than I thought.
Not a 90.
Oh, I don't suppose there'd be one of those other browsers on this machine. No. Ooh, too much to expect. All right. Well, there was part of my talk.
Didn't you have some videos on that?
I do have videos.
That page.
On that page?
Yeah. Where you just worked.
Where I just was. Oh, yes. Okay, I could try that.
I.e.
There we are. That's not it.
You can try with the lamp, hopefully.
Up there on top I saw video.
Yeah. Okay, this is good. This will be an old video, but we can try it. What? A little help here? Okay, maybe not. Okay, well, maybe I won't show it.
What about the other four?
Try the Vimeo version.
Video? This
Try
one?
the Vimeo. Just go up to the app, play it.
The player here? Okay, try that. See what happens.
There you go.
And how do I expand?
Right there. Right next to the Vimeo.
Sorry. There you go. Okay. Anyway, so this is more or less what you see in an older version of this thing. This is probably a topic of news or something, and these are all being clustered together. And so what you'll see there are various topics coming in. Each tweet that comes in has the associated icon associated with it. Each cluster has a variety of terms that we've determined is kind of most identifying and shared amongst those various tweets. All right. And then on the left-hand side of here, very hard to see, is a timeline, historical timeline. And so, in fact, you'll see the running tweets coming at the top, and each one as they come in, you'll see the slide expands up to show what the tweet looks like. And as I mentioned, you have the timeline on the left here, where you can see the number of tweets coming in over a period of time, and you're able to move the cursor down to various things and check these things. I'm not too Well, yes. So, for example, here's a case where you can click on one of these things and go right to the particular article that I was referring to. I'm not too concerned about not giving you this demo right now because, in fact, this is all online, and I'll give you the URL at the end, and you can play with it to your heart's content and see what was really going on. Okay, this is a rough idea of what's happening, and so let me now stop this and go back to the talk before I get any deeper in this thing. All right. Okay, and back to view. Okay, so that was the demo. Anyway, so we put this together, and it's currently being used by several organizations within AT&T. And this is where I again making confession. Another example where my ability to predict things that are popular is totally wrong. I mean, I really felt there was nothing in this thing, and yet it has become very popular within the company, and they're using it in all sorts of places. For that matter, I didn't think Twitter was going to take off either. So there you are. I mean, so in fact, if you want to make money, find something that I think is not going to work, and put it on the opposite, and you'll be set. All right. Okay. So rough architecture in this piece of work. It's largely broken into two pieces. One part that's doing the data collection from the Twitter part, and the other part that's actually doing the major analysis and visualization stuff, which is then get pushed out to the browser. So the data collection part uses one of the standard API provided by Twitter. So you're allowed to ask for all tweets containing one of up to 400 keywords. Or if you want, you can actually get 1% of all tweets. Or if you want to pay a lot of money, you can get a lot more than that. But there are various interfaces that Twitter can provide you. And the data is stored permanently, so we can do this historical checking, running back in time and looking at things that had occurred in the past. Okay. The other part is then this upper check type pipeline up here, which is doing the analysis, the visualization. Okay. And basically, it starts with the raw tweets. It does a semantic analysis, very cursory, trying to get some information, some way of putting these tweets together. Uses that to kind of construct a graph of relationships, and then does this business about the analysis and the drawing and the clustering and the mapping stuff. So what I want to do in the rest of the talk is more let's dive into these things in a little bit more detail. Okay. As far as the semantic analysis text part goes, as with any of the things, the first thing you have to do is clean the data. All data is dirty. It's going to have stuff you don't really want to use that's going to lead you astray. So you have to remove all the various markup notations in this thing, all the things telling you about retweets and references to other people. URLs need to be removed because typically they're truncated and they don't have a lot of good information in them. And also these things are going to have lots and lots of stop words that are just no semantic information whatsoever. So you got to get rid of thes and as and ands and that type of stuff. Okay. All right, once that's done, then we want to construct the similarity matrix for the data. To construct a graph on the various tweets making relationships. The process we use is the term frequency inverse document frequency. It's a mouthful, all right. It's actually very simple. It's basically the term frequency is the fraction of times that a particular term appears in a document. And the inverse document frequency just takes a look at this other term of basically how many times a document contains a particular term over all the documents in that particular class. And then the IDF number is simply the product of those two things. And to get a document similarity, we can simply take the cosine of the vector, where you hold one of for the two documents, you look at all the vector formed by over t, take the cosine, and that gives you a notion of similarity. This gives a very dense matrix, and so to kind of clean it out a bit and not have too many edges, we put in a threshold, found that 0.2 kind of works nicely to get rid of the really weak edges. You don't want these to be too much cluttered. We did look at a more sophisticated technique called latent tertiary allocation. This is a much more sophisticated and potentially more accurate approach to getting a similarity matrix. But we basically found that it tended to be too sophisticated. And especially since in this case you're dealing with very small messages, only 140 characters, so you can't say much. And if you have so you can't rely on too much information. It's like when you're trying to do decryption. If you only have a bit of text, you can't really do a good job. You need a lot of text to make it worthwhile. And similar thing here, this thing is too expensive and it tends to get misleading clusters. Whereas this thing certainly guarantees that any messages within the same cluster at least share some terms. Okay, so the next step then is to take the similarity matrix and use that to get the obvious graph. So if there's a non-zero value on the entry of the matrix, that's an edge. All right. Here we're starting to get in toward the hardware. We're looking at the amount of space we have on the display to use, and so we figure you typically see up to 500 tweets per given window on a browser because that's where it's going to be displayed. Now the layout part of it at this point is done using a combination of multidimensional scaling, and then to do overlap removal, we use the Prism algorithm that was described in graph drawing 4 years ago. And then finally, we just once we've got this layout and all this thing moved, we take this layout and use that to create a graph, a map, very similar to the one described earlier. And that was based on this GVMap algorithm that Stefan Kobourov and Yifan Hu and I described in this article here. So what you get is something like that, as you saw earlier. So this is you have basically a collection of countries, and this would have been water otherwise, and just puts together that thing. Okay. Up to this point, this has been totally a static description of the algorithm, but obviously this is a stream of data coming through, so we have to handle that. And what we do is basically update the information roughly k minutes. We started with one was about a little bit too much, so we went to about 5 minutes. That seems about right. And we're trying to preserve the user's mental map. And so to do that, we first of all start by rerunning multidimensional scaling using the previous positions, or if we enter new tweets in, we use the positions related by the average of the neighbors. And that gives a fairly stable display in terms of the relative positioning. However, you do tend to get some things like rotations and other things that come involved. And we want to match we want to keep it very stable, so we have to figure out how to get it back to the way it was before. And to handle that, we do a Procrustes transformation. So basically, we're looking for a scaling, a rotation, and translation to take the new drawing and make it match the old drawing. And that's a well-known problem. So the solution is here, where the x and y matrices are basically the n/2 versions of the xi's and yi's. And so this gives us the translation. This gives us this gives us the rotation. This gives us the translation. We actually have decided to just use the scaling as 1 because if you don't do that, you tend to start introducing node overlap again. Since the nodes are not points, but actually take the space, we need to keep them separated. And in fact, for heavy streams, trying to preserve the mental map is actually isn't that important. If you've got lots and lots and lots of messages coming through, basically the topics are going to come and go. And so you almost have to, every so often, just toss out the entire thing and start over again anyway. So this is more important for ones where we're changing more gradually over time, like visualization, which I would have showed you. OK, so there's one thing that we still need to handle in this thing. And when we took that threshold to 0.2, that oftentimes takes away enough edges, and you get actually a disconnected graph. The graph I showed you wasn't fully connected. So you have these countries which really aren't connected, and you need to pack it in there. And we have to figure out a way to handle that, because as time goes on, you have this problem that, OK, well, you now redraw the graph, and now you've got this overlapping. Well, you now have to remove that somehow. And the standard packing algorithms don't necessarily preserve the relationships. Like, for example, here, this is to the, here, we got next move to the left, and it all gets messed up. What we'd like to do is be able to take these components and reposition them so we have we removed overlap, but we have roughly the same layout as we had earlier. OK. And so that the solution we did this is to take the prism algorithm we used before to remove overlap, but to extend it so it handles non-rectangular shapes. And instead of just worrying about getting rid of overlap, we're also going to be using it to remove space, to pack things more tightly. OK. So it's done reasonably simply. Instead of just using rectangles, we use polyominoes to represent the nodes and edges and use that for collision detection. We want to kind of reduce the graph, the problem down to a tractable form. So to do that, we use a proximity graph, in this case, the line triangulation for scaffolding. So that gives a nice rigidity, and it also gives you a very sparse graph to work with. In that case, all we're going to do now is for each of the edges in the proximity graph, we check for the endpoints, and we map all the polyominoes down to that line. And either there's going, so this is kind of the left-hand side of the green part. This is the right-hand side of the blue point. So either there's going to be overlap, in which case we want to push them apart, or there's going to be this extra space there, and we can pull them together. So it'll be one of those two situations where you either have an overlap or a gap. OK. So how to solve that? Well, what we want to do is we set up an ideal length factor to be that extra either gap or overlap we're trying to handle. And we now want to create a new layout with these edge lengths, basically either removing the gap or expanding to get the distance. And of course, for us, typically, OK, we want to do something. We all, MDS is all we know, so we pull out MDS and get the same problem, and we just pack it in there, and we've got the ways to solve it. We solve it. All right. This almost works. Slight problem is that, as with most of these things, if you just apply it straightforward, you get too fast of moves, and you'll break up the proximity and the relationships that you had. So the way to do that is to kind of gradually add in this extra information. So what we do is we damp the movements. Instead of using this raw T here, we use kind of a scaled version of T, and we pick these to bound it. And so we iteratively keep moving it until there aren't any more any problems in the layout. So that, again, mostly works, except that once you've gotten done and you've gotten taken care of the proximity graph, you look at the drawing and you say, oh, there are still overlaps. That's because some of these things are going to have large, bad aspect ratios, which you didn't take care of by the proximity graph that you constructed. And so then you have to add a little bit of more extra information. So we put some more edges in here into the proximity graph to handle those situations. And then we just do this. So here's the first loop. Here's the second loop. And we run it. And again, there's no proof that this works, but basically in principle and by practice, it seemed to do the job. So an example, this is the algorithm we call StayPack. This is the initial configuration. And after one iteration, we get this. Second iteration, we get this. And finally, a third iteration, we have the separation. So the areas are now more or less where they were before, rough proximity, but they've been moved apart, but without a lot of extra space. And if we apply that to the full display, so here would be one situation. Now some more things pop in, so there's a slight adjustment, pretty stable, but there's been some changes. Now some more ones are coming in down here. They'll fill in some spaces. And again, you have a very, very small adjustment as time goes on, as each of these comes in. And again, I mentioned that after time, there will be enough changes where you simply can't have stability anymore, and you throw up your hands and say, okay, forget it, I'm going to start afresh, and you just dump everything on the floor and start with a new display. Anyway, so as I mentioned before, you can do your own demo. Please go to this site and try that, and then we have the various versions, and you can try the various options and play with them. It's available, and well, we've done various changes to it, and in fact, it's still being worked on. So it might, in fact, may break when you try it. Anyway, thank you.
Questions for Emden?
So in the visualization, the edges are not very readable. Do you consider them not so important? Or?
Yeah, basically, if you can zoom in and get more detail on these things. You can click on the things and do exploration down that. But at this high level here, we don't view them as being particularly important. The main thing is the clustering at that point. But yeah, if you want to delve into more detail, that's possible.
I like it. If you're really looking at temporal sequences over a long time, are there ways that you can identify critical moments to look at?
I guess the definition would be what would be critical. One thing we have seen is you will, in fact, I mean, one easy way is if you look at the timeline on the left, every so often you will see a big peak. And that's when something important has happened.
Right.
And
so there may be spikes in certain terms,
yeah.
Or so that may be one indicator of particular frequency. The other sort of thing is what happens as, I may have missed it, but do clusters reform, regroup, and split?
Yeah, there will be this constant motion of clusters because as tweets come in, whole topics will disappear, new topics will form. Some tweets from one cluster will now, in fact, be part of another cluster. Yeah, that will be a constant changing going on.
Yeah, okay.
Yeah.
So, all right.
And certainly it needs to be, if you're really trying to analyze the data, you'll need lots of other tools that you want to run in conjunction with this thing to get the thing.
So, what's the corpus for the TF-IDF scores? Just the history or all that you've seen so far?
There's a window. We use a particular window. I forget the exact size of it, but yeah, you keep shifting that window, and then you're doing the analysis of that. And even the summations we use for the timeline. If you pick a point, you want to see the keywords for that particular moment in time. That's in fact a totally different calculation of the TF-IDF based on another window.
Peter.
I know this is a T2 paper, and I'd like to ask a question on behalf of the T1 people in the audience. So the map is essentially a planar graph. So why don't you use planarity-based methods?
Because the map isn't. Well, I mean, the map isn't a planar graph.
Dual of a planar graph.
He's saying if you think of the countries as
yes, but the underlying tweets themselves are very heavily connected and very non-planar.
The representation is planar.
The representation is planar of the countries, yes. So what would you have us do?
Filter out a planar graph and draw the planar graph.
I thought you said no more planar graphs. We have
That's right.
4 more years of planar graphs. Other questions? I forgot to mention that this is indeed a T2 track paper, and in fact, the best paper award was given to that paper, so congratulations.